the end, so I have some notes. It's my pleasure to introduce today's speaker, Professor Samar Safi-Harb from the University of Manitoba, where she's a Tier 1 and research chair in extreme astrophysics that you see on the screen. Some of her members are online. She has broad interests, as you will learn in her talk, and she's involved in myriad missions bringing in data about the extreme universe. Prior to Manitoba, Samar was a NASA fellow at Goddard Space Flight Center, and then before that she did her graduate work at the University of Wisconsin-Madison. And before that, she was at the American University of Beirut for her undergrad. And I didn't get to ask you, but did you know our former CITA fellow, Shihad Tuma?
Oh, yes. Oh, that was a CITA fellow.
Yes.
What a small world. I had no idea.
There we go. So let me go into the small world. Shihad is a dynamicist, and he was present here around 1995. Who else was here in 1995?
96.
Johnson
96.
Was here. James Wadsley and Chris Thompson was just leaving or about to leave for North Carolina, so it was a momentous time. I mentioned Doug and James and Chris because they've spent a lot of time together the past few days in the CITA Council meeting. And in the CITA Council meeting, Samar was the chair. So I could digress further and tell you about others in 1995, like John Tsai, who's Anna's father. It's not here. Dimitri, for those of you in Alberta. Dave Charbonneau was a summer student, and so on. So my conclusion is that it's a happily connected world. And let us enjoy Samar's presentation. Thank you.
Thank you so much for this wonderful introduction. Maybe I can add a little bit of my personal connection to Toronto. Maybe nobody knows this here, but actually, when I wanted to go for grad school, I applied to U of T because I had my brothers here, or one of them went to history. And so that was a natural place for me. And I was accepted and I got excited. My government promised me a fellowship to do grad studies in North America. So I went to them and they said, no, you can't go to U of T because if you go to Canada, you'll never come back to Lebanon. So I said, okay. So they gave me 10 options. One of them was Madison, Wisconsin, which I went to partly because it was about a 12-hour train ride to Toronto, and which I did a lot. Actually, I wrote a lot of proposals on those train rides. It was very efficient for me, but also because I was very interested in particle physics, particularly neutrinos. So I was really attracted to the research program of Francis Halzen, who's well known in the neutrinos. He didn't have funding for me, so by accident, I ended up being an astronomer, not a physicist. So I went to a physics department. And then when I went to Goddard, I had this wonderful Canadian office mate. I was still in my second year of postdoc at Goddard, having a wonderful time there. But he told me, Samar, there's this new opportunity. He knew I wanted to go to Canada. So he said, there's a new position in Winnipeg to start an astronomy program. And I said, that's great. Where is Winnipeg? so I didn't know about Winnipeg. Of course, I knew a little bit. But so that's how I ended up in Winnipeg. Really, I was very excited about this challenging opportunity, and I'm someone who likes extremes. So from extreme hot weather to extreme cold weather, I can survive. So that's kind of my story. I think I also applied to postdoc at U of T, but I ended up going to. So I've always felt connected to Toronto, and I love the people here, and I'm so glad to be here and to see that the department is growing. Lots of wonderful new people that you're hiring, and to see this breadth and diversity of research areas. I'm very fond of Chris Thompson's work on magnetars, Peter, your work on ISM And now I'm glad to see gravitational wave with especially Maya and Reed. So hopefully there will be more connections down the road. So what you're seeing here, lots of pretty pictures, and you're gonna see lots of these. Each of these is a supernova remnant, and each has a story to tell. And I love working on these objects because they allow us to probe the physics of supernova explosions and supernova progenitors. It's very hard to do it when looking too far. So this is, I focus on sometimes individual objects to understand the fundamental physics related to nucleosynthesis and particle acceleration. So there will be two parts in my talk, and I'll talk a little bit about the zoo of neutron stars and compact objects, which could be a whole talk by itself, but I won't focus too much on it. I'll just use the zoo of compact objects to connect it to the question of nucleosynthesis and supernova progenitor science. I have to acknowledge my wonderful collaborators. There are too many to list here, but these are very close collaborators of mine, and of course my wonderful group members shown here, some of whom are online, so help me out if any questions is related to your work. This is color-coded, so you see it's a very diverse group, and it's color-coded by the wavelengths they work on, and white actually means they work on everything, or also known as theory, or modeling, numerical simulations. Nathan and Labani, CITA National Fellow, and Nathan, they work on gravitational waves and are in the LIGO scientific collaboration. But yeah, so I have people who work, so we're a diverse, multi-wavelength, multi-messenger group interested in the physics of compact objects and supernova remnants. So why should you care about supernova remnants? If you care about galaxies, nucleosynthesis, particle acceleration, and compact objects physics, I think supernova remnants are wonderful nearby laboratories really to allow us to probe this physics. And we are in a very exciting era of multi-wavelength, multi-messenger astronomy. Here I show some of the Nobel Prizes given to Riccardo Giacconi for X-ray astronomy, Anthony Hewish / Jocelyn Bell for the discovery of pulsars and radio astronomy, Nobel Prize for gravitational wave detection with LIGO, the discovery of cosmic rays, and of course neutrinos to our Canadian Art MacDonald. I want to touch, a lot of what I'm going to show you focuses a lot on the X-ray part of the electromagnetic spectrum because of the subject I'm going to be focusing on, but I'm going to touch a little bit on other wavelengths. And in terms of the synergy with other messengers, it's not talked about much when we talk about multi-messenger. We often think of gravitational waves, but I really want to touch on this part, which is also, there's a lot of exciting science happening in gamma ray astronomy as well. So to do a little bit of history, we just celebrated in Sweden this past summer 100 years of supernova discovery. Although we all know of these famous people, Bad and Zucchi, who in 1934 said that supernovae make neutron stars just 2 years after the discovery of the neutron and cosmic rays. And they actually cite in their paper back then Landmark, who's this Swedish person who 100 years ago, that's the 100 years of supernova discovery, has advanced this new class of supernovae at the time called upper class novae. And he's among the first people who pointed towards linking the 1054 record to the Prague Nebula. Moving on to more on the historical aspect for compact objects, so pulsars and magnetars, which have a lot of applications to other areas in astronomy. So, of course, the discovery is credited to Jocelyn Bell, who accidentally discovered them when she was building a radio telescope working with Anthony Hewish to work on quasars. But of course, she found these pulses of light, which were named pulsars. And it was this theorist, Franco Caccini, Italian, who in 1967 as well advanced the view that these are rotating neutron stars, which are powered by the rotational energy. So as they rotate, they slow down. This rotational energy loss goes into magnetic dipole radiation, and this is how we infer their magnetic fields. They turn out to be about 10 to the 12 Gauss, very strong magnetic fields. But then there's this gentleman that was very familiar to you, Chris Thompson, who worked with Duncan, and they introduced the very exciting topic of magnetars, the strongest magnets in the universe. When they were trying to understand how magnetic fields in neutron stars form, they said we can easily achieve 10 to the 15 Gauss.
10 to 16.
16 now? Okay, 10 to the 16. I guess from observations we've seen 10 to the 15, so maybe we didn't get their observation yet.
Well, the big flare.
Yeah.
You need more than 10 to 15.
Yeah. But it's just an order of magnitude. Among astronomers, it's okay. But I believe it. So they're still the strongest magnets, and they're bursting sources, and they're becoming, like, people don't care too much sometimes about pulsars, but now there's fast radio bursts, and there's a connection to magnetars, because one galactic magnetar showed evidence of fast radio bursts. So now, like, the whole community is really watching more for magnetars and neutron stars. And of course, neutron star mergers also made us go back to the physics of neutron stars. So why do we care about supernovae? They also make the elements essential for life, as Carl Sagan said it very eloquently, but I also want to point out our Manitoban star guy, Wilfred Buck, who I was very happy he got the Cascade Kellogg Award for all his work on indigenizing astronomy, and I'm very proud that I work with him. Feel very privileged to indigenize astronomy into our curriculum. But I also want to point, I was talking to Chris the other day about connections to Winnipeg and Al Cameron. Who knows Al Cameron? Or, yeah. Okay, so this is someone who actually introduced the R process to explain the formation of the heavy elements in supernovae and even neutron star mergers. Everybody knows about the B2FH paper, which is the Burbage, Foil, and yes, I know it as B2FH. So anyway, so Al actually worked independently on the same thing. Should be credited. I mentioned him because he's a Winnipegger. Okay, so
Chris.
yes, that's why
We went to the same high school.
Yes, we went to the same high school, so that's how we were discussing it. So, so really great people from Winnipeg. So, so let's talk about the supernova classification. I'm heading into the zoo, right? So traditionally we classify them based on their optical spectra. This is the old Minkowski and Zwicky's 1940s classification based on the absence or presence of hydrogen in their spectra. But we know in terms of the physics, the 1As are the thermonuclear explosions, and the others are all core collapse explosions. So there's already a zoo, and this is the very simplistic way of looking at it. And even among the 1A class, there are lots of models which can be broadly classified in terms of the progenitor into single degenerate and double degenerate. The single degenerate means there's only a single white dwarf accreting matter from a companion star until its mass reaches the Chandrasekhar limit, and then that leads to the explosion. Double degenerate, we have two white dwarfs, sub-Chandrasekhar mass, which eventually explode into this type 1A or thermonuclear explosion. In terms of the core collapse, we believe that there are explosions of stars more than 8 times the mass of the sun. And despite the Crab Nebula being the most famous, heavily studied core collapse explosion in our galaxy, we still do not understand the explosion mechanism of this object. Almost. We have to do it by 2054, okay? So come with you. Mark your calendar for the 1000th anniversary of the Crab. So supernova remnants are fascinating objects. We can image them thanks to all the wonderful telescopes on the ground and in space now. And they can last for thousands and millions of years. So they are our opportunity to really understand the progenitor and the explosion mechanism by just looking at this, this wonderful gallery of supernova remnants. And I want to advertise our high-energy catalog of supernova remnants, SNR CAT, which has in it everything you need to know about any remnant. In our galaxy, we're up to 400 now and counting. And I'll show towards the end an updated version of that. But this has been used as a database for the supernova remnant community. Each entry has in it everything you need to know about every remnant. And I'm very happy also to say that we're using it for search for continuous waves in neutron stars and supernova remnants. So it's also serving the LIGO scientific collaboration because we have all the parameters needed for the frequency, for the parameter search for continuous waves. So, so let me talk now, show you some pretty pictures. So these are very historical type remnants that have been witnessed by various cultures. So they're very young. One of the big questions in the community, what type of explosions they are. We believe they're type 1A for various reasons that I'll get into shortly. But some of the hot topics right now is like, are they single degenerate, or they double degenerate, or something else? There are other models that are still being proposed. And some remnants tend to be somehow have this 1A with big question mark classification. So one of the things we do in my group is really try to classify these objects using different methods, not just a single one. And in terms of the core collapse, so that was thermonuclear. In terms of the core collapse, now we see that there is lots of different objects that are powered by different types of neutron stars. So the traditional one is like a probe powered by a rotation-powered pulsar. But with magnetars now, we have about more than a dozen supernova remnants which are housing magnetars, those neutron stars which are powered by their magnetic field decay. And Chandra led to the discovery of the central compact object right near the center, which was previously missed in this commonly believed to be a core collapse supernova remnant. So we call it central compact object for the lack of a better name. And we also have pulsars which are called high-B pulsars, which are highly magnetized, but their magnetic field is intermediate between the rotation-powered pulsars, which is about 10 to the 12 Gauss, and magnetars, which is about 10 to the 16 Gauss. So these have magnetic fields intermediate, close to the QED line, where you expect to have magnetar behavior. In fact, they recently showed us that they also emit magnetar-like outbursts. So they look like rotation-powered pulsars, but occasionally they burst into magnetars. This is a very dear topic to me, but I won't talk much about it other than saying that we have this zoo of neutron stars. So it's really natural to ask the question, is this zoo of neutron star really related to the zoo of supernovae? What are their progenitors? Can we tie the progenitors to the supernovae? So this is one of the questions I want to address. Yeah.
One often hears about accretion-induced collapse of white dwarfs. Is there any direct evidence in terms of remnants for this?
Yes. I mean, we don't know for sure, but we're looking into those types of things, and I'll show that we can never say for sure, but there are hints for that. I'll show you some examples shortly. So basically, this is the classification which I'm talking about, the zoo of supernova. And if you're a supernova researcher, this goes all the way down. There's lots of subclasses, and these are some examples of these core collapse or type 1A supernovae that have core collapse that host a zoo of neutron stars. So the question is, can we connect the progenitors to the supernova type? So now let's move to the techniques that we use to typing supernovae from using supernova remnants. So one method used is light echoes, which was advanced by Armin Bratz. Basically, when supernova happen, they travel to us, but they can also travel and take some detour and scattered by dust. So sometimes when we see the echo much later, which gives us the spectrum, which tells us something about the type of the supernova. The most trivial, easy way to classify supernovae as core collapse is to find the central compact object or a pulsar with nebula, which tells us immediately there must be a core collapse supernova. And in X-ray imaging and spectroscopy, we have now new tools by doing some population study, which is a very small sample still, but it's big for the supernova, galactic supernova remnant community. So what this shows, the luminosity of the iron K line, which is around 6.4 keV, or in that range. And then the red are the type 1a and the blue are the known core collapse. And so you see there's a clear distinction between the two. In other words, the core collapse tend to show a higher centroid of the iron K line. And that's because we have higher density associated with the core collapse. So lower ionization state can imply lower densities, which is typical in type 1a supernova. So this is one method. So if you're unsure about your supernova, you find iron K line, you put it on this plot. Where does it fall? Then you could say if it's a type 1a or core collapse. There's also studies of, yeah.
You say higher density, do you mean in the stellar atmosphere?
The ambient density in which they're expanding. Yeah. Yeah, feel free to interrupt me. I like to be interrupted. So the second one is on the morphology. So you look at the whether they're symmetric. I showed you some pictures. Some of them are quite symmetric and some of them are very messy. So the belief is that the quite symmetric ones are more type 1a and the messy ones are core collapse because they happen in messy regions as well. So that's again showing that there is roughly clear distinction between the two types. And a very powerful tool, which I want to focus on next, is comparing the spectra, X-ray spectra of supernova remnants to nucleosynthesis models. Okay, so basically we believe type 1a, they are more iron rich. So this is again X-ray spectra from 0.5 to 10 keV. And we see elements like oxygen, neon, magnesium, silicon, sulfur, iron, and nickel. And so the oxygen-rich ones tend to be more core collapse, and the iron-rich ones tend to be the type 1a. So we look at their spectra and try to compare them to nucleosynthesis models based on the progenitor. So thanks to a golden era of X-ray astronomy, which started with the launch of Chandra and XMM 26 years ago now, they're still functioning really well. So we can really zoom on those supernova remnants, but also get very high quality spectra. And now with PRISM, with Canadian participation, launched in 2020, a couple of years ago now. So we have also very high resolution spectra. We have also NuSTAR, which was launched a decade ago. And this is great for looking at the hard X-ray emission from supernova remnants. And just when James Webb Space Telescope was launched, we also had XP, which is the X-ray polarimetry mission, which is looking for X-ray polarization, which tells us about the magnetic field in these objects for the first time in X-rays. So thanks to this golden era of X-ray astronomy, now we can really address these questions. So from modeling X-ray spectra, nucleosynthesis comparison, I just want to highlight the methodology we use in our research. So this is an example of the Cassiopeia A supernova remnant. So we basically have a forward shot going into the interstellar medium and a reverse shot going back into the ejecta of the explosion. So both are shock heated. Thanks to Chandra, we can resolve these. So we can actually resolve the ejecta from the supernova explosion. So that's the first step. We look for the ejecta-dominated supernova remnants. We separate the ejecta from the ISM, and then we model them, right? So we model all these elements from oxygen all the way to iron in the X-ray band, which allow us to determine the abundances of those heavy elements. And then the theorists give us, based on different types of explosion models, and there is lots of them, we have predictions on nucleosynthesis yields for both 1A and core collapse. So using those yields, comparing them to the fitted abundances, we can infer the progenitor mass as well as the type of the explosion. So this is just an example spectrum of the Cassiopeia A supernova remnant from Chandra.
Samar, sorry, can I just ask, how do you know something is ejecta dominated?
Very good question. So, so actually, this is a color-coded image, and I'll get to, in the second half of my talk, this blue one is all non-thermal synchrotron radiation, but this is all thermal, and the color refers to the energy band. Mm-hmm. So we know oxygen is in the lower energy, soft X-rays, and then you have neon, magnesium, silicon, sulfur, and iron. So this is all iron here. So the color actually reflects the element. And when we fit the data here, like the fit tells us that they are enhanced above solar abundances. So when they're above solar abundances, we know that they are ejecta. So both from doing the imaging part as well as So we believe in the case of gas A, this is actually where the forward shock is going into this interstellar medium and the density question you asked. And this is the reverse shock heat ejecta going into the remnant. And so here is a gallery of type 1A supernova remnants. So we're going to apply this method to a set of type 1A supernova remnants and core collapse supernova remnants. Okay? And we're going to be a bit selective because we want the good quality data, right? And we want the ones that are ejecta dominated so we can do this exercise, right? And it's a PhD thesis, so it has to be done in a reasonable time scale. So this is actually Cole is defending this thesis this Friday. And this is the gallery of remnants he worked on. And one of the main goals of his thesis is really to do this systematically. So in the X-ray community, you pick your favorite remnant, you pick your favorite model, you pick your favorite element, and you say, it's a single degenerate. In the core collapse community, we do the same thing. Whoever is your friend, you pick their model, and then you actually try to fit, and it's a 25 solar mass progenitor. No, it's a 50 solar mass progenitor. You see conflicting papers with different results. So we decided to do this systematic study, same methodology, all nucleosynthesis models available to us, all of them, for core collapse and type 1A. So Paul did his PhD on 1A, and the next one I'll show you is on core collapse. So we fit it. As expected, none of the models fit all the methods, right? Some models favor some elements. So it works, but not quite well. So this is just an example of a supernova remnant, a type 1A supernova remnant. We're doing the exercise. This is core collapse. So this is the data, and these are the models. These are core collapse models. You see clearly that really is bad. So good, we classify it as a type 1A, which is the better one. But then it doesn't seem to work for all the data points, right? So again, this is the data and this is the model. So it doesn't work for all of them. There's something about the models that doesn't work perfectly, which is expected, but then what can you do? So our work is meant to help improve the people doing the modeling, but also we have caveats in our analysis in that, the quality of the data, and also this is a time-dependent evolution, so it depends on which time and the evolution of the supernova remnant we're looking at. So this work is meant to really help advance the theoretical as well as the data quality for the future. I want to go back to the iron K9 spectroscopy. So I mentioned that we see a clear distinction between the 1As in red and the blues, right? And so these are 1A and this is core collapse. So we decided to revisit this for some of the remnants that are a bit questionable. And one of them is like right at the edge, like this guy, right here. And there's this other one which has also unknown classification, another galactic supernova remnant. So it's like 1A with a question mark or core collapse with a question mark. So first, when we look at this comparison with the nucleosynthesis models, we find that overall the thermonuclear or type 1A fits better than the core collapse overall, although it doesn't work perfectly well. And same thing for this one. So it seems like the 1A seems to fit better than core collapse, but obviously not quite well for all the elements.
So a number of the type 1A models involve a two-stage process, first with helium and then with CO ignition.
Right, this is the double detonation.
Is there any evidence in the remnant abundances for some substantial amount of helium burning product?
Yes, not in these spectra. So we have a JWST approved program actually for one Kepler to actually look for that, into that question.
Excellent. So that is an active investigation.
Yes, active investigation. So yeah, so what I'm trying to address here is the elements that we can see in the X-ray spectrum, which is from oxygen to neon. But these models take those reaction rates into account. So there's obviously nothing seems to be work, but these tend to be classified as 1A based on, or thermonuclear based on this, right? Now let's look at the other messages, because I like to look at the problem from different perspectives and see if they actually agree, and it turns out they don't agree.
So just to be clear, before you go on, this would suggest that W49 should be made red.
According to this, yes.
Yeah,
Thank
okay.
you for following. So this tells you that this is in the wrong place first, right?
That suggests.
Suggest. And this one, look what it is. It's at the border, right? This at the border always bothered me. Now, when we look at the iron K line for this guy, which is at the border, we find when you do spatially resolved spectroscopy, so thanks to Chandra and XMM, we can actually look at regions and determine the iron K line. When you average it out, you end up on the left. But actually, it's going from left to right. So what do you believe? So, I mean, life is complicated. It cannot be as simple as just one single iron K line. So when you average things out, you get the wrong answer. So there is some kind of tension between what we get from spectroscopy using this comparison to nucleosynthesis model versus the iron K line. And as you clearly pointed out, there's also a problem with morphology. The reason that guy was on the right is the morphologically it looks. So morphology, spectroscopy, iron K line are not giving the same answer. So something is wrong. Yeah.
There's a tremendous range of luminosity there.
That's another.
Is that age or density of ISM that they're plowing into, or what?
That's a very good question. I think it's about the brightness as well of the object. So you tend to get a much brighter line when you have more brighter objects. Now these ones here are very young. So yeah, bright could be because they're very young. So this is one of the youngest type 1a remnants, same thing for Cassiopeia A. But they're not all young, like there are older objects. So it's not purely age. It could be also because of density. So the higher the density, the higher the luminosity, because you have a higher emission measure for the plasma. So that means a denser medium.
But it's interesting that the type 1As, which on average should be in lower density environments,
Right.
have the same range of luminosity as the.
Exactly, and that could be related to the double degenerate versus single degenerate, right? Because they should be different mediums.
But the density you're talking about here is the stuff that came off the supernova, not the interstellar medium into which it's plowed.
Actually, so yeah.
If you're measuring the synthetic abundances, that
Right.
must be the
Yeah.
ejected dominated gas.
Right, yes.
Not the local molecular cloud or whatever it's hitting.
Right, but I mean, this ejecta is expanding into the medium. So I'm talking about the medium in which it's expanding, where the ejecta, it's in the immediate environment of the object. So if it's expanding into a cavity or a bubble, then you expect the luminosity to be extremely low. And lower ionization timescale, lower iron K line essentially. So the 1As tend to go in this direction and probably to the lower part. But actually, as you clearly notice, that some of them are high, and that could be, we actually have evidence that some of these, especially this one, has some circumstellar medium, denser medium with which it's interacting, which gives us some insights into the different types of 1A progenitors as well. Right? They cannot all have the same ambient medium.
I think I remember IC443 as half of it in a molecular cloud and half is.
Exactly, yes. And this is the same for this object actually. There's a cloud here, that's why there's a very sharp edge, so it's much
So
denser.
the spatially resolved.
Right.
Very interesting for various of these.
Exactly, yeah. So we're pointing out that spatial results gives you a different answer. This relates to all your questions. Kepler, this is believed to be a type 1A, but it's obviously not spherically symmetric. It has this weird bipolar type structure, which based on morphology, you would, if you didn't know anything about spectroscopy, you would immediately classify it as a core collapse. And in fact, some people, there he's calling you. Oh, now I lost my screen. What's happening? Stop.
Well, it doesn't have to be.
Is it?
So this the same as reset as we did at the beginning?
Okay now? Yeah. Should have turned off my phone, yeah. Okay, so I guess they had a question on Kepler. So Kepler is a very interesting topic. This is the one where we have, by the way, JWST time on, as well as CITA on CFHT. It's a very exciting target from an X-ray spectroscopy perspective, looking at those abundances. You see a problem with both, but this seems to be the best model, which actually refers to this data point here, this model, which is actually a double degenerate supernova. Okay, obviously it's not perfect, but it's double degenerate. And if you kind of also go into more details, what type of double degenerate? It's called D6. We think, so this is again part of Paul's PhD work, we think it's a D6. So now moving to the numerical simulations aspect to say, okay, can we learn anything about it? And this is work done by Gilles Ferrand, who was, by the way, CITA fellow as well, CITA national fellow. And so he works on 3D simulations of supernova, following them from the supernova stage going into thousands of years. Very computationally intensive. And so he worked into this problem of D6, which D6 stands for dynamically driven, double degenerate, double detonation. And why is this? This is becoming a very interesting type of model because with Gaia, Shen et al. Have discovered 3 hypervelocity white dwarfs. And they have been suspected to be resulting from a double, from this D6 model. Because in that D6 model, the white dwarf actually survives. So we commonly thought that double white dwarf, double degenerate, they actually both are blown away. But in this particular model, the white dwarf survives, it acquires a very high peak velocity. And they found evidence of 3 hypervelocity white dwarfs that might be attributed to this type of model. So we are interested in this for various reasons, including what I just showed on the previous slide. But this is kind of the simulations, and this shows, at about 1,000 years, how the model in terms of the density looks like from 3 different projections, X, Y, Z, to show that there is some kind of shadow that's left from this white dwarf that survived. And then as you evolve it with time, it reflects itself on the supernova remnant. So suddenly you start seeing all these new structures, which look like, lobes or centrally filled type morphology remnants. Some of the remnants are called mixed morphology because they're centrally filled, just like this one. We used to think they might be corpulabs, but in fact, no. This is a result from the simulations that show that we are really naive about how we interpret the morphology of remnants. We should really compare them to simulations. And now there's ongoing work in collaboration with Japan on actually making predictions, not just on the morphology, but also on the spectra, so we can compare directly the spectra with high resolution X-ray spectroscopy to the results of simulation, not just from this D6 model, for actually all kinds of 1A.
So it becomes more centrally filled as time progresses?
Yeah.
Why?
So I think it also depends on where you're looking at it from. I think because also it's becoming brighter, right? Like as it evolves, it's plowing into the interstellar medium as well. So it's becoming brighter and brighter, and you're shocking more ejecta. Obviously, the reader shock is hitting more. So I think it's just lighting up more of the ejecta. And but this shadow effect becomes noticeable as you go.
So this might be then a reverse shock effect?
Yes, yeah. So we stop at this age because beyond which you start mixing everything with the ISM. So this is still an ejecta-dominated phase. But the bottom line from this is to say that 1A explosions do not have to be spherically symmetric, nice, uniform. They can look like those mixed morphology or messy-looking remnants. So I want to move, so that was a lot on type 1A. I want to move to the core collapse. And I talked about the zoo. There's magnetars and central compact objects, right? Magnetars are the highly magnetized neutron stars. Central compact objects, I forgot to mention, they're on the opposite end. They're sometimes referred to as anti-magnetars because they have much lower magnetic fields at least from the three which have measured spin down, right? So the question is, what type of progenitors? Can we say these are from very massive progenitors, these are from very low mass progenitors, as some people said in some papers? Again, systematic study. And what we find for those very handful of magnetar hosting supernova remnants that have ejecta in them, where we can do this comparison to nucleosynthesis models, we find that they're around less than or equal to 20 solar mass progenitors. So not necessarily as high as previously reported. I mean, we also reported some papers in the past where we say they are very massive, like 45 solar masses, but based on the sample we use, we find, so which means that there is a whole range of masses based on these models we're using. But the other interesting thing is that the energies are actually low, at least, this is a factor of 10 lower than what you expect from the kinetic energy of supernova, so they're not very high. They're not very high means that there is not much energy injected by this rotating neutron star, which then suggests that there is no evidence for fast millisecond proto-neutron star in the magnetar hosting, which is something that's proposed for gamma ray bursts outside our galaxy. That to explain the GRBs, you need very fast spinning proto-millisecond neutron star magnetar. But in this case, if there were millisecond magnetars, you expect that energy to be dumped into supernova remnant, unless they're going into something else like gravitational waves. Then if it's going into the remnant, there's a problem with the energetics.
So how many are really down toward 10 to 50?
Sometimes we find even lower than 10 to the 50, a few times 10 to the 49. So yeah, most of them that we worked on are around 10 to the 50. And that's a problem that we're kind of putting forward also for the people doing nucleosynthesis models, because they always assume 10 to the 51. I see some people thinking, great. So for the CCO hosting SNRs, again, this is the subject of PhD work of Chelsea Brown, former PhD student now. She did this same work that I mentioned for core collapse, but hosting only the central compact objects, and these are some of these objects which are ejecta dominated again, right? We do the suite of nucleosynthesis models, including, so we've been working closely with Chris Fryer, who's been adjusting all his models to adapt to the data. Nothing is working, so he keeps pushing the other theorists to do the same. And so none of the models fit all the metals. We find evidence, again, of low energy explosions for the majority, and we explore the effect of the degeneracy in the explosion energy on the effect on the data. So this is, again, to put forward the need for improvements in the modeling aspects, considering asymmetries, the effect of metallicity, different explosion energies, as well as the need of better high-quality data. And I want to reiterate the point that X-ray astronomers tend to introduce bias when selecting their favorite models or elements to the data. So it's all about removing that bias. Okay, so now I want to move on something, still the same topic, which is addressing the progenitors of supernova remnants, but moving away from the X-ray band. I know there's a big community in Canada who love the optical, and we have CFHD, which has CITA, which provide integral field spectroscopy. So we do some of this research to also address the same question. What are the progenitors of this zoo of neutron stars? And here I just want to highlight this very interesting remnant to the high energy community, because this remnant was first discovered in the 90s with ROSAT. And then actually this is a picture of Vela, the famous Vela supernova remnant. This is Pappas A, another one. And this is, if you look at it in hard X-rays, you start seeing something here. If you look at it in TeV gamma rays, you don't see much of Vela except for Alpha, but you see this object that they call Vela Junior, just because it's smaller and it looks like it's in front of it, and it's a cool name. And this is CITA, which is now doing survey like ROSAT, but wider energy band and more sensitive. And if you can look closely, I don't know if you see, this is Vela Junior, you see a very clear shell. And inside there is this central compact object. It's a point-like source seen only in X-rays. So those central compact objects are really seen only in X-rays. There's no counterpoint at any other wavelength. And 3 of them have very low magnetic fields. That's why they're called antimagnetars. So what are their progenitors? Can we do anything about it in the optical? Nothing is done outside the X-rays for these objects. But I want to highlight this important remnant because it's important to the high energy community. It's one of the most particle accelerators. It's one of the brightest TeV gamma ray sources, and there's not much in it in thermal X-rays. It's mostly non-thermal synchrotron radiation. So there's something unique about it as a pevatron source, which I'll get to next. But it has also the central compact object. So it's completely different from Cassiopeia A. Cassiopeia A is also has a central compact object, but it's full with ejecta thermal X-rays. So completely different beast. So what can we say about the CCO? To address the environment of the CCO, so to address the progenitor, we're going to look very closely to the environment. This is the subject of the PhD work of Janet, who's doing her work on integral field spectroscopy using NEWS and CITA for southern and northern sources. And so this is just to introduce this technique. It's a wonderful technique. Basically, this is very small field of view. So this is our remnant. The remnant is way bigger than this whole slide. And this is the central compact object, and this is where we looked at. So it's really the environment of the central compact object, which has seen only in X-rays. Now we see this little nebula around it, and for every speckle or for every little dot on this image, we have a data cube, which has in it velocity information and position. So we get basically the abundances, the velocities, and the morphology all at once. And this is illustrating that this nebula actually turns out to be nitrogen-rich nebula. So this is, again, the CCO from X-rays, and this is the nebula with an H-alpha, a bright H-alpha shock-like structure. And so this is the first optical nitrogen-rich nebula, which, when we use mappings to model the actual chemistry in this, we infer a mass for the progenitor of 60 solar mass. So it suggests a Wolf-Rayet star progenitor, which is creating this nitrogen-rich environment in which the supernova is expanding and which can be photoionized by the hot central compact object. So more evidence for this Wolf-Rayet star is coming. So looking now, zooming out from this using NEWS again, there's this beautiful picture where the colors are, again, red is H-alpha, and then we have a very rich nitrogen environment. And so this is, again, the CCO that I was talking about. There is this interesting thing. What is it, do you think? Dog or no?
Looks like a Herbig arrow.
Exactly, it's a Herbig arrow object. It was misidentified before, and there's this discovery of Herbig arrow object. Now, if you look at the chemistry of this, it turns out to be very similar to the chemistry that we see around the central compact object. So morphologically also, there is some evidence that there is some kind of interaction. So we just had this paper accepted for FJ letter where we put forward the idea that these are two in the same place, and they are both, this Herbig arrow object is actually enriched by the nitrogen-rich environment created by the massive Wolf-Rayet star progenitor. And why is this interesting to us? Not just because we are linking star death to star birth, but also because now we have an accurate measurement of the distance to this object because we have a parallax distance measurement. How often do we have a distance to a supernova remnant determined from parallax? Never. Well, there's Vela, but there's Vela Junior now. So this is, again, saying that now we have a very accurate distance measurement, putting it actually much further, way beyond Vela. So we called it Vela Junior. This name has to be changed, no longer Vela Junior. It's behind now Vela, and it's a bit older than what people thought. But given the age now, we can, based on the proper motion of the velocity seen in X-rays, now we have a measurement of the velocity. It's 7,000 kilometers per second. We have a measurement of the age. It's 2,000 years old. But we also have a measurement of the ambient density, and it's 10 to the minus 3 per cubic centimeter, extremely low density, which explains why we don't see any thermal X-ray, which explains why it's so bright in non-thermal X-ray emission, and which is consistent with the massive progenitor idea, Wolf-Rayet, creating a cavity in which this is expanding. So it's really solving the puzzle for this very important remnant for the high energy community.
But are we somehow looking very specially along the plane? Because why did these two things
Exactly.
Why were you so serendipitously lucky to find this?
Very lucky. Yes.
You just think that's it?
I hope so. But we're very excited about the distance, and Maya, the LIGO people will be very excited to have such a narrow range for the distance and age, which we'll use for really constraining the search for continuous wave from neutron stars and supernova remnants. So the distance measurement allowed us to determine a lot of the properties and solve the puzzle for this particular remnant. But to go back to my main question, the progenitors of central compact objects, we're saying here it's a Wolf-Rayet progenitor. That is most likely the answer. Of course, we need to look into more evidence for that. So that's it for the nucleosynthesis part. There's a Pevatron's part, but I don't have much time on that.
You got about 5 minutes.
5 minutes. Okay,
But
so I'll tell
you
you.
can have more because of the lengthy introduction.
Lengthy introduction.
Technical
Thank you.
difficulties.
Thanks. So I can skip a few things, but maybe you can tell me what are you most interested in this particular question. Yeah.
Sorry, I'll come back to it later.
Yeah, you had a question. Yeah. Okay, so pevatrons. Pevatrons are the sources that accelerate cosmic rays all the way to PeV energies, which is around 10 to the 15 electron volt. And so this is a very active area of research, especially for the gamma ray and high energy communities. Of course, cosmic rays were were proven to used by Victor Hess, who got the Nobel Prize for it. And now the big debate in the community, are they leptonic or hadronic? Leptonic means accelerating electrons to these ultra-high energies, which would manifest themselves in synchrotron radiation in X-rays and inverse Compton scattering in gamma rays. But if they're hadronic, cosmic rays are mostly protons and nuclei. So we're looking for hadronic emission that would manifest itself into secondary synchrotron radiation in X-rays, which would be probed with missions like New Star X-ray satellite, and pion decay in the gamma rays. So supernova remnants have long been thought to be the primary suspects for pevatrons in our galaxy. I mentioned this golden era of X-ray astronomy, but I would say that New Star has really advanced our view of this field in the X-ray band. And in gamma rays, it's really blooming. They started with only a few sources, the crowd and another one, decades ago. Now they're talking about a population of dozens of sources, and that's thanks to the advance of the imaging atmospheric Cherenkov telescopes like Veritas and HESS and MAGIC, which are imaging supernova remnants with arc-minute resolution, so it's still not great. But we also have these air shower arrays, especially Hawk and Lasso in China, which is making amazing discoveries of these pevatrons, discovering PeV photon energies. Like, they're finding PeV photon energies. And so this is just to show you the current state of gamma ray emissions in terms of their sensitivity and energy coverage. And this is the future for gamma ray, the Cherenkov telescope array. But Lasso is the one that goes really high in energies. So supernova remnants have long been thought to be the ideal sources because energetically they can do it. The way we discovered evidence of hundreds of TeV electrons in these supernova remnants goes back to the ASCA days, where supernova 1006 was discovered in pure non-thermal X-ray emission with these two bright rings, which coincide with TeV gamma rays. And so if you have hundreds of TeV electrons in micro-Gauss magnetic field, you get photons energies of the order of 20 keV or so. So when we look at these in hard X-rays and find non-thermal X-ray emission, it's evidence of synchrotron radiation from hundreds of TeV energies, which implies a particle population of the order of PeV energies, or pevatrons. The big question is, are they leptonic or are they hadronic? We cannot really necessarily address this question. And the other thing is, the cutoffs in most of the X-ray spectra appear to be short of the PeV energy. So let me jump on Lasso. Lasso is now advancing our view of pevatrons, discovering lots of these sources, many of which are associated with supernova remnants and pulsar wind nebula. We're looking at a big sample of these as pulsar wind nebula, and we're finding, I'm going to go very quickly with this. This is, by the way, in collaboration with Kaya Mori, who I learned recently was also at CITA. He's
Yes.
in Colombia. a great collaborator, and so we're doing a lot of work together also on Pevatron. So we have this huge campaign looking at pulsar nebula, supernova remnants, lasso sources in X-rays to actually pinpoint the location of the acceleration site and model them across the electromagnetic spectrum, SED modeling, to address the question of hadronic versus leptonic. So what we're finding is pulsar nebula are consistent with being leptonic pevatrons, but I want to move to the microquasars, which is really now what's exciting the high energy community. So the latest lasso, the previous map was from 2021. Now we are in the latest one, which actually showed evidence of some 40 plus pevatron sources, and some of which are microquasars with energies going up to PeV clearly. So microquasars are now competing with supernova remnants as potential pevatrons.
That like SS4, that kind of source.
That's it, spot on. SS433. So before I show you this, so this is the LASSO recent finding of 5 microquasars with energies going up to close to several hundreds of TeV. And the first suspect is SS433, and this is called the Manatee Nebula. As you clearly see, the connection. So there is this interesting source, SS433, which is a high mass X-ray boundary, and it's called microquasar because it's emitting jets moving at quarter times the speed of light. And those jets, as they go hundreds of parsecs, they actually inflate this nebula that we call W50, and this is the ear. So really, this is the impact of those jets on hundreds of scales. So it's a micro version of an AGN, where you also see such slopes on kiloparsecs or megaparsecs scales. This is my favorite source in the galaxy, not because of this picture, but I worked on it during my PhD days with ROSAT and ASCA and RXTE, and I actually found evidence of hard X-ray emission, very hard spectral index of 1.5, which is insanely hard for an X-ray, synchrotron X-ray source. And I just quote myself here because I'm proud of this. I suggested in 1999 that W50 is an important site of acceleration of cosmic rays, and it should be a pevatron candidate. And I think the gamma ray community have been looking for evidence of that for 2 decades. So I slept on this source for 2 decades until they found it. So in 2018, there was this Nature paper where Hawk discovered, now it's tilted because it's different coordinates, but this is SS433, and this is the contours of the X-rays. So they found evidence of TeV emission clearly aligned with those X-ray knots or lobes. And now there's another source that's being called W50-like, which is called, this is a very important now source as well that we have a huge campaign to follow up on. But I want to say once this came out, we came back to W50, and we have now a huge campaign to look at the source with the modern missions, everything you could think of. So, so we know that these are pevatrons because you see the energy spectra go all the way to PeV. And in fact, the LASSO collaboration proposed that SS433 is even a hadronic one because you need a hadronic component to fit this hard tail in the LASSO spectra. So it's becoming a real possibility, but I want to highlight the work done by my student Ryden. I'll show next a better image. But this is, again, W50 multi-wavelength image. The red is radio. The purple is really XMN data, which also coincides with the new star. And these are the ears, right? So the first thing you notice perhaps is these sharp edges. There's nothing in between. So this is SS433, which emits just on small scales, and then nothing in between, and then there is the sharp shock. This is where the hard X-ray emission is. So we think we probed the region, the acceleration region that emits those TeV gamma rays. And we call it the head. So the head is where the particles are being accelerated, and we believe this is what's responsible for the TeV gamma rays that are seen. So it's really a sharp shock seen in hard non-thermal X-rays described by a very hard power law index. We even have an estimate of the magnetic field and the energies to which this is. And this seems now to be consistent with what has seen TeV gamma rays. And that got the attention of ESA. They call it cosmic manatee accelerated particles from the head. Except our head is not here, our head is here. And so the other really exciting thing is that X-ray now allows us to determine magnetic field in terms of polarization degree and magnetic field direction. And this is the first time in X-rays that we can actually do that. So this is again the XMM image that I showed earlier. It's just an intensity image. The XP region that we studied showed that we have actually a polarization degree that should be a dash from 38 to 77%, and that the magnetic field is actually aligned with the jet. So this is the jet, this is the magnetic field direction. So it shows that it's clearly aligned and extremely highly polarized. So it's highly ordered magnetic field, which is something we've seen in pulsar ring nebula, and it's seen also in FR2 jets in radio. So this is kind of shedding light on the acceleration mechanism, and we're following up with newly approved observation on different parts so we can actually constrain the acceleration mechanism across the lobes. And one exciting thing going back to progenitor science, by looking at the whole northern part of the remnant with XMM, we found evidence in collaboration with Chinese collaborators, we found evidence of thermal X-ray emission from the north, which overlaps with the radio shell. And one of the big questions about W50, is it a bubble blown by the SS433? Is it just a wind-blown bubble? Or is it a remnant associated with a black hole? And so we basically find evidence from the X-ray spectra that we have a constraint on the age and the explosion energy of this supernova remnant, which is consistent with the radio study as well. So if this is true, that would be the first direct observational evidence of a black hole supernova remnant. And I just can't resist but show you this beautiful multi-wavelength upgraded image. And this is work done by PhD student Bryden, who's working on microquasars from small mass scales to all the way to AGNs. But yeah, this is again highlighting this northern shell. And we're going to be looking next at this part, which is still missing. So V4641 SGR, I'll just say very quickly, this is another extremely exciting source. SS433 is a high mass X-ray binary. This one is a low mass X-ray binary, but it has superluminal jets, and it actually goes into outbursts occasionally. But it has this morphology like W50. It seems to have this double lobe structure that, as seen in Hawk, has an lasso barely. I mean, you can see the effect of imaging resolution, of course, has the best we generate. But now the big question is this like W50? We have a whole campaign following up on with Chandra, XMM, Newton, and USTAR to answer that question. There's also Meerkat data coming in radio to address that question. But that's like the next hot object among the lasso sources that we are pursuing. We use PRISM Extend to actually look for any evidence of X-rays. We found some evidence, but I won't necessarily bore you. This is a bit too detailed. Addressing the question if it's hadronic or leptonic, we don't know the answer, but we have this multi-wavelength campaign, so stay tuned for the results on that. So to conclude, I would say supernova remnants are really nearby that to help us address the physics of supernova progenitors, both in terms of the explosion mechanism and the progenitor type. Imaging and spectroscopy are helping shape the field for next steps for numerical simulations since stellar evolution, as well as stimulating 3D simulation of supernovae into the supernova remnant phase to make predictions on the observables. Integral field spectroscopy is opening a new window into understanding the progenitors of high energy objects, traditionally studied only in high energy. While supernova remnants and pulsar wind nebula remain viable candidates for being at least leptonic pervatrons, microquasars are now the more popular sources among the gamma ray community. I want to mention that SNRCat has been used as the basis for multiple studies of individual objects as well as population studies. And I feel like this is a service to the community, for the international community, that's kept up to date. And it's being upgraded in this new multi-wavelength, multi-messenger era. And this is a montage which is put together by other grad student, Austin McMaster. This is showing you the current status of SNR and CAD. All the gaps are being filled in with the new images, which is obtained by Meerkat. So we're using a lot of the radio surveys, and SKA will help a lot in these ventures that we're basically developing it to become more of a service to the multi-wavelength, multi-messenger community. And finally, I want to just talk very briefly about something I'm really excited about, which is the next generation X-ray mission. I'm sorry you have to leave, and I'm sorry I went over time, but this is making the point that we really need an X-ray mission for the 2030s, not just to follow on the legacy of Chandra and Swift, which are nearing the end of their lifetime, but also to serve the multi-wavelength, multi-messenger community, and AXIS will be the one. What is AXIS? It's the Advanced X-ray Imaging Satellite. PI is Chris Reynolds from the University of Maryland. We had a proposal, so this is one of the 2 competing X-ray probes. It was selected for phase A study, and it's planned to be launched in 2032. The concept study report due to NASA in early 2026. We're trying to get CFA involvement in this mission because there's a lot of Canadian interest in this mission. But AXIS is really going to advance Chandra in terms of imaging resolution across a large field of view, but also it's going to be a super Swift, and it's going to be a community facility with more than 70% of time for guest observers. So it's going to be matching Chandra's resolution across a wide field of view, but also it has an incredible survey grasp. There's lots of surveys being planned, including a galactic plane survey. So it's not just Super Chandra, it's also Super Swift, which means it's going to be great for transient sources. And putting it in the context of other NASA missions. So right now we're down to Chris as the latest X-ray mission, but there's nothing being planned in terms of X-rays. Of course, we have these amazing things being planned, including Lisa and Roland soon, and we have LSST. So we need something in X-rays that really matches the resolution, and even look for the X-ray counterparts for all these sources. So I would say AXIS is needed. There's a lot of synergy with everything you can think of across the electromagnetic spectrum, also with gamma rays, cosmic rays, gravitational waves, and neutrinos. This is a plot from a recently submitted to the archive 600-page AXIS Community Science book with lots of Canadian participation that shows you the variety of topics being addressed by AXIS, as well as all the synergies mentioned in this book. So it's on the archive. Pick your favorite topic and look for what AXIS can do. So I'll just end by saying we are truly in a very exciting era of astrophysics where we can do not just multi-wavelength, but multi-messenger, with a lot happening in the other parts of the messenger space in terms of gravitational waves, neutrinos, and cosmic rays. Thank you.
That was a great talk.
Thank you.
We interrupted you a lot with questions.
That's great.
You have the energy to answer a few.
I have lots of energy
Well,
left.
people can,
Yeah,
there's
lots
a
of
few
great
cookies
questions.
upstairs.
Just a quick comment. When constraining rotation in supernova cores, one has to be cautious. There's a simplifying assumption that's almost always made that you just have a solid rotator that's collapsing, and then you have a monolithically rotating protoneutrons. But we're learning that supernova explosions are very dynamic. A lot of the rotation, in many cases, may come from the last tenth of the solar mass of material that
Okay,
collapses.
so not from the, so
And
you're
so
addressing the
if I
energy.
take, for example, a tenth of a solar mass shell, rotating 3 milliseconds, right, it will mainly share its angular momentum with the rest of the star before the exterior. And then you end up actually not much more than 10 to 50 years in rotation energy being positive. So there's a lot of room for very dynamic differential rotation in supernova
That's
cores.
a very good suggestion and point. So you're basically saying that the low energy explosions do not rule out the proton neutron star. You're saying that
They
energy
don't
can
rule
go.
out
Yeah.
having some significant rotation and some subcomponent.
Yeah.
of the proton.
Okay, that's good.
And, you know, one sees in supernova simulations now very strong asymmetries that could produce
Right.
such sortation.
Right, so we should look for